This lecture will discuss a brief history of and the discovery of radioactivity alongside the chemistry involved in the nucleus when radioactive decay happens. So radioactivity was discovered in around the early 1900s. So the first high energy rays that were found were X-rays, and these are actually not radioactive. These are a type of electromagnetic radiation. So they were called X-rays by this man because he didn't know what they were. And this is the first ever X-ray. He was playing around with them in his dark room, and he decided to use his wife's hand to block the source of the rays, and he found that the bones appeared and the ring, and then you can barely see the skin around the hand because this part of the hand was not, it didn't quite reflect the rays the same way that the bone and the ring did. And so he figured that some sort of electromagnetic radiation caused this, and he just named it an X-ray. So another group was trying to figure out what was going on with those cathode ray tubes and was interested in the X-rays and ended up finding uranium crystals. And this guy had wrapped them in some cloth and then put them on top of film, and he found even when they were not exposed to the sun and wrapped in cloth, that they could cause a shadow to appear on film that had been kept in a locked drawer for several weeks. So he and Marie and Pierre Curie started their work in 1898 trying to figure out what all of this was. And these two actually named it radioactivity, and they shared the 1903 prize with this guy here. And Marie and Pierre Curie continued to work on this for the rest of their lives until they died of cancer, most likely caused by their research. And Marie Curie's notebook is still emits unsafe levels of radiation to this day. So when we say radioactivity or radiation, we mean something different than the types of rays that are emitted by the electromagnetic spectrum. So that is light and radio waves and X-rays and ultraviolet rays and all of that. These are different. They have a different source. These come from the nucleus. And we are going to talk about three different kinds of radiation: alpha, beta, and gamma. Alpha particles are the largest, but alpha particles are the largest, although they can be stopped by something as thin as paper. So your clothing or gloves are going to prevent these from penetrating your skin. Beta particles do need a bit more. They can be absorbed by thin layers of lead, and gamma rays are high energy. These are much more dangerous, and because they can cause the compounds in your body to break down and become ions, and they require a much greater thickness of lead to stop the radiation. So we're going to talk about alpha particles first. It is composed of two protons and two neutrons. So we're going to talk about alpha particles first. They are composed of two protons and two neutrons. So essentially, it is a helium nucleus. Now, it's not a helium atom because there's no electrons here, and it's not its own little particle. This is something that would be kicked out of the nucleus of a very heavy element. Something like uranium, when it's undergoes radioactive decay, can kick off an alpha particle. So it's going to lose essentially a mass of 4 and a charge of 2. And so we can write it just like this, like we do with isotope notation. So since an alpha particle has a mass of 4 and a charge of 2, we can write it this way. A beta particle is a sort of electron that gets ejected from the nucleus. And so we write it like this because it doesn't have a mass, because it's an electron, and remember it's like 0.0005 for the mass of the electron compared to proton or neutron, but it does have a full charge of -1. And so essentially what's happening here is the neutron in the nucleus has a small positive and negative particle inside of it. You can kind of imagine it that way. So like think of it as like one of those little plastic Easter eggs. And you have two little beans inside of it, and you shake it around, you can hear it. So the neutron has those two pieces inside, and you crack the neutron open or crack the plastic egg open and spit out one of the beans, and now there's only one bean inside. So that's kind of what's happening here. So essentially, what we write it like this, and the net effect is the nucleus. In the nucleus, you now have one fewer neutron and one more proton. So there's no change in mass because a neutron and a proton have the same mass, but they don't have the same charge. And so that's how the charge goes down by 1, but the mass doesn't change. The last bit of radiation is a gamma particle or a gamma ray. I don't really call these gamma particles. I've always called them gamma rays. And what they do is it has so much energy that it knocks electrons out of atoms in matter and makes ions. So like this really can mess up your DNA. It can destroy proteins. It can be really damaging to cells and living tissue. So we can write equations to show how these things break down. We know the law of conservation of matter, so we can't create or destroy matter. And we also know that even though John Dalton wasn't 100% correct when he said that the atoms couldn't be subdivided, because they can, but he was right in saying that the mass would have to be the same before and after. And that's true here too, mostly. So they have to have the same number of protons and neutrons on both sides of the chemical equation. So if you look here, we have this sample of uranium-235, and I'm calling it that because it is the element uranium, and its mass is 235, and it has 92 protons. And so it has, you would have to subtract 92 from 235 to get the number of neutrons. And then if it emits an alpha particle, like it does over here, we see that now we have this alpha particle and this element, which is thorium, named after Thor of mythology. And if we look at these numbers here, 231 plus 4 is 235. 90 and 2 is 92. So the mass hasn't changed. The mass is the same on either side of the arrow. But this is our parent, and then it breaks apart into two daughter pieces. So this is like the daughter nucleus, and then this is the alpha particle. We can practice by writing the nuclear equation that represents the radioactive decay of radon-222 by alpha particle emission. So we start with an atom of radon-222, and this is the most stable isotope of radon, and it's actually the most implicated in human health risks because it is found naturally when uranium decays, and it can build up in minerals and rocks underground and in mines. And there are some areas of the world where you have to have detectors for radon gas because it can cause lung cancer. Because as it breaks down and you get exposed to the radiation, the half-life is at least a day. So you get exposed to the radiation of this compound, and it is the second leading cause of lung cancer following smoking. So it is something that if you buy a house ever, or if you live in like a basement, you want to check radon levels. So we have our isotope written here. It's radon-222. 86 is its atomic number. And then I'm going to draw my arrow. And now we see decay. which means that we're going to start with one particle on the left and it's going to break apart into two pieces or more. And then we see that alpha particle emission. So I'm going to go ahead and just write in my alpha particle of my helium nuclei with the 4 and the 2. And so then remember that the masses have to be the same on both sides. So all I need to do is subtract 4 from 222 and I get 218. And then I subtract 2 from 86 and I get 84. And then I look at my periodic table and I see that element 84 is polonium. So we can do a similar thing with the emission of a beta particle. So the overall mass number will stay the same, but the number of the protons technically would increase because what's happening is a neutron is being turned into a proton. So in this picture down here, it kind of illustrates, here you have your carbon-14 nucleus, it undergoes beta decay, and now you have a nitrogen-14 nucleus and an electron. And we can write electrons in that atomic nuclei notation as a 0 and a -1 because this is the charge and this is the mass. And then we see that if we have 14 and 14, they're the same and 0. And then here we have 6, 7, and -1. So if you add these together, you get this number here. So we are still adhering to the law of conservation of mass, and we can use this notation to show how beta decay happens. So in this, we did radioactive decay of radon-222 earlier, and so we get alpha and gamma radiation emitted. And so this gamma radiation is actually where we get a lot of negative effects on humans or other life. So that this gamma radiation has a lot of energy. So 8.2 times 10 to the minus 14th joules per nucleus. Now, this isn't a huge number, but it's per nucleus. So if you have a small sample of radon decaying, you can get 49 million kilojoules, which is a lot of energy. So to give you an idea of how much this energy actually is, 1 joule is the energy needed to raise 1 gram of water 1 degree Celsius. So it's not a huge amount, but water has a really high boiling point. So think about like every time you increase the temperature of water by 1 degree, and that's only 1 gram of water, which is equal to 1 milliliter of water, right? So you're raising a milliliter of water 1 degree, and that's how much a joule is. So you can see how that might add up really quickly. So let's do some practice here. And we can say that we have this boron 12. So boron 12, and boron is element 5. And then we know it's going to be beta particle emission. So we can put our electron with the 0 and the -1. And then we're going to keep that 12 because that's a 0 and we are not changing the overall mass. But instead of 5 protons now, we have taken a neutron and turned it into a proton. So now we have 6. So a mass of 12, proton of 6, that is carbon. We will talk more about this quantity of atoms later. That's not really important right now, but know that it would be around 50 million kilojoules. So we're talking a lot of energy that's going to be released by that decay, by a small amount of radioactive decay.